So, hi everyone, glad you found this room, and we are very happy to have here from next door from Radgers, who will tell us about single source shortest path.
Okay, yeah, thanks so much. Hi everyone, thanks for inviting me. Yeah, so this is joint work with Daniel Pandangankai and Christian Wolf-Olsen. So let me just start with introducing the problem. So the problem is a problem you've all heard of. Just you have a graph, you have a source, you want to figure out shortest path from the source. You can also just think of this as ST shortest paths. Everything ends up being the same. So classic results, basically if your graph is unweighted or has non-negative weights, this problem is easy, you run Dijkstra's. But the moment your graph has negative weights, this problem becomes much harder. And so it's the sort of classic algorithms you learn in undergraduate algorithms with negative weights. You can see it's a good deal slower. Okay, so there has been some improvement here. So what is the history of the problem? So again, this is the problem we're trying to solve. And basically there's this MN time algorithm, this classic MN time. And this is actually still the best known if your edge weights are arbitrary. But we don't know how to beat MN for arbitrary. Unlike for like non-negative weights where we can use Dijkstra's. So basically all subsequent work made this reasonable assumption that your edge weights are integral and they're polynomial in N, and then you can use various scaling techniques. And so then the history kind of breaks down into three phases. There's kind of the classic phase where people came up with this original MN time algorithm. And then this is kind of the best known for a while. And then there was this kind of flurry of results that improved upon this using various combinatorial tools in like the 80s and 90s. And then for a long time, this remained an open problem. It was sort of a big question. People are asking, can you beat M-root-N? M-root-N was also bound for many other problems like bipartite matching. And very recently, there was kind of this sequence of breakthroughs using a completely different set of techniques. So they're not really combinatorial. They're using continuous optimization. They're using various dynamic data structures. And they tend to be much more involved algorithms. And so there's this kind of sequence of improvements in this line, but it's still not quite down to linear. And finally, there are some special cases that people were studying as well. So basically, the result we have is, first off, we kind of settle the complexity. We really get it down to near linear. And also, our algorithm, interestingly enough, is not really following this kind of more recent trend and is much more similar to these algorithms here. So it just kind of uses elementary combinatorial tools, and it shows that's actually enough to get near linear time. Okay, so I want to quickly talk about, though, at the same time as our result, there's an independent result, this like really amazing breakthrough in graph algorithms, where they solve a much more general problem. So they solve like min cost flow in not quite near linear, but close to linear time. And so that as a special case implies our problem. And this is based much more on these kind of continuous optimization dynamic data structures method. So as I said, these were done independently, but now that the second result is out and we have this min cost flow algorithm, I want to talk a bit about how our result then kind of fits into the general perspective. I think that if you set the capacities to be infinity and you just have demand 1, you just have to route 1 unit of demand and it's uncapacitated, then essentially you're finding the shortest path from S to T. I agree that, and if you want to do single source shortest, yes, yeah, you can have negative costs. Yeah, exactly. Yes, your costs are just exactly the weights in the graph. Yeah. Okay, so basically, now that we have this min cost flow algorithm, the kind of general situation for graph algorithms is there are all these really basic fundamental graph problems, many of which we teach in undergraduate algorithms. They're really easy to define, and stuff like bipartite matching or max flow. And for many decades, we didn't really know how to solve them, and now we have a fast solution for them. But it doesn't quite feel like we're done because this fast solution is incredibly complicated, uses very heavy machinery. And for a problem like shortest paths or bipartite matching, it feels a little weird that you have to use such heavy machinery and many intricate algorithms to get it to work because it's such a simple to define problem. So it feels like the next step is to kind of find algorithms that are basically simple, stuff that we can teach in an intro grad class or something. And there are kind of two reasons you might want simplicity. One is just simple is nice, but another reason is that simple algorithms are much more likely to work cross paradigm. So generally, if you wanted to have like a streaming algorithm or parallel algorithm, you kind of start with the normal sequential algorithm, you try to port some of the ideas over. But it's very hard to port the ideas of this algorithm because there's basically just too much going on. It's not going to be possible to get it to work in the parallel setting. Whereas simple algorithms are going to be easier to port. But yeah. Yes, it's also like integer cost polynomial and n. Yes, absolutely. Yeah. Okay, and so basically the takeaway of our result is, all right, so we figured out how to get like a simple fast algorithm just for this particular problem, but it would be interesting to see if you can do that for other problems on this list. I think probably the next natural goal would be bipartite matching. Yeah. Absolutely no formal notion. The only form, I mean, you can sort of say like our algorithm is combinatorial. Now that you can maybe more formally define combinatorial. Simplicity, I have no formal notion. But I think like I've talked to the authors of this paper, like I don't, they wouldn't disagree with me. But no, it's totally informal. Yeah. So yeah, there's a lot of judgment calls to be made. Okay. So let me now talk about how we actually get the result. So let me start with some preliminaries. So kind of a weird talk to give because because it's relatively basic, I'm just gonna try to give you the whole algorithm. So it'll get a little technical. But all of this stuff is pretty basic. So if something isn't making sense, it's just because I'm not explaining it well. So definitely stop me if some definition doesn't make sense or anything like that. Okay, so just some simplifying assumptions I'm gonna make for this talk. They're all without loss of generality. I'm gonna assume the graph doesn't have a constant degree, and I'm also just gonna assume the graph doesn't have a negative weight cycle, so we don't have to worry about that. So we can assume that shortest paths are well defined because there's no negative weight cycle. Okay, so there are three basic preliminaries I want to define. The first is price functions. This is very old preliminary. So the definition is, probably many of you have seen this at some point, but it might have been a long, long time, that given any graph, you can define a potential function on the vertices or a price function on the vertices. This essentially corresponds to dual weights, but I'm not going to do it from an LP perspective. I'm just going to define it straightforwardly. So if you define any function on the vertices, then you can use that function to change your edge weights in this very natural way. So why would you want to do this? Well, there's this basic lemma which says that if you have any graph and you take any such price function and you change its weights in this way, the shortest paths don't change. Like all the edge weights change, but the shortest paths remain the same. And the proof is just a telescoping sum. Basically, if you look at the original path and then you look at its reduced weight, this like price weight, then essentially all the terms cancel and only the first and the last term remain. But the point is this first and last term are the same no matter what XY path you take. So basically all XY paths, their weight changes by the same amount. So whatever was shortest in the original graph, still shortest. Okay, so what is the idea of using price functions? So this is the takeaway that you can use as many as you want. The shortest paths are never going to change. And so the idea is that we're going to try to find a good price function. Like essentially the way to solve this problem is you want to find a price function such that all the edges become non-negative under that. So you want to find a specific potential on the vertices that has this nice property. And once you do that, you're done, because then you just run Dijkstra's on this graph. It has non-negative weights, and it has the same shortest path, so you're going to get your shortest paths back. Okay, so the point is, if you could compute a price function, it's easy to compute shortest paths. This sort of goes in both directions. If you have a graph with negative weights, and you can compute shortest paths in that graph somehow, you can actually use those to compute a good price function. And all you do is you're going to create a dummy source S with edges of weight 0 to every vertex. And then you're going to compute distances from that dummy source. Again, I haven't shown you how to compute them, but I'm just saying if you could compute those distances, then you would get a good price function. And you just set the price of each vertex to be the distance from that dummy source. And then triangle inequality just immediately implies that all the distances are not negative. You can just stare at that for a second and you'll see that that's what you get. So the takeaway is that we're going to sort of go back and forth between price functions and distances constantly. And I also want to highlight now that basically for the rest of this talk, I only care about the dummy source S. So in theory, this talk is about, given some input source, how to compute shortest paths from that input source. but you just ignore that input source will not figure in the algorithm at all, because it only figures here. Like at the last step, once you have a good price function, you run Dijkstra from the input source. But the whole point of the talk will be finding that good price function. And there, when we work with a source, we're always just working with a dummy source. The goal is you just find your price function, which is not source specific. It's just a price function that works for all the edges. And once you have that, you can then run Dijkstra from whatever input source you want. Okay, so S is always going to be a dummy source for this whole talk. Okay, so second preliminary. Again, back to stuff that you all know, but maybe haven't thought about for a long time. So we have a Dijkstra, works well if edges are non-negative. Bellman-Ford is much slower. But Bellman-Ford works quickly if every shortest path contains at most gamma edges, because you just run Bellman-Ford for gamma iterations. Okay, in fact, you could show something more general, which is that if every shortest path contains at most k negative edges, basically positive edges are easy. So as long as every shortest path contains at most k negative edges, you can again have an algorithm that runs in mk time. This is, I mean, we proved this in our paper, but this is basically folklore. Very easy algorithm. You just like basically run Dijkstra. If the green edges are non-negative, you run Dijkstra, and that gives you the shortest path up to here. Then you run one iteration of Bellman-Ford, that takes you up to here. Then you run Dijkstra, that takes you up to here. Then you run one iteration of Bellman-Ford, that takes you up to here. You just like combine them in the most obvious way, and this algorithm will come out of it. Okay, and we actually will prove something slightly more general, which is that if the average vertex has at most k negative edges from S, that's still good enough. You can still get an mk time algorithm. I'm not going to prove this, but again, just combine Bellman-Ford and Dijkstra. Okay, so these are all. So why do we need this algorithm BF plus Dijkstra? So basically, what this tells us, the takeaway, is that it's easy to compute shortest paths if they contain few negative edges. And so remember, our final goal is to find this good price function. And in the good price function, all edges are non-negative. But instead, what we're going to do is we're going to have an intermediate goal, which is we're going to find a price function such that we will have a small number of negative edges, but there will only be a small number of them. And in particular, we're going to guarantee that on average, every shortest path has few negative edges under this intermediate price function. And the point is, if you have this, you're done. Because once you have this intermediate price function, you can use this Bellman-Ford plus Dijkstra to compute actual distances. Because again, if there are few negative edges on every path, you can easily compute distances. And once you compute distances, as I said before, the moment you can compute distances, then you can get a good price function. So we can think now that we have this intermediate goal. We want to find a price function where paths have few negative edges. Okay, so those were the two kind of very old preliminaries. Those were like from the 60s and 70s. There is one tool that we use that's a bit more modern, but still goes quite a far way back. So it's basically a way to decompose a graph into a bunch of low diameter components. So I'm going to define it first for undirected graphs, just because it's more intuitive, and then I'll show you how to define it for directed graphs as well. Okay, so this is just a black box statement that, so you're given an undirected graph, and this only works for non-negative weights. And basically what this is saying is that you can decompose your graph into a bunch of connected components and a small number of edges crossing between the connected components. So basically you can find a set of bad edges, ESEP. Think of this as like E bad. These are bad edges, such that if you delete the bad edges, then all of your connected components have small diameter. And the point is that you can do this very quickly. And so I said that we want the number of bad edges to be small. In fact, you can show a much stronger guarantee that basically says every particular bad edge is bad with some small probability, where the probability is basically the weight of that edge divided by D. So if D is big, then you're allowed to have big components, and then you have even fewer crossing edges. And so that's why the probability goes down the bigger D is. Okay, so that's how you define it for undirected graphs. So this is like a very old, this decomposition has been known since the 80s. And it's used a bunch in parallel and distributed algorithms. It's also used for like tree embeddings, like embedding a graph into a tree metric. You use these kind of decompositions. So it also ends up appearing a lot in approximation algorithms. So this has been used for a long, long time. But now I want to talk about the directed version. So basically this statement was known again for a long time. The directed version is similar, but hasn't been used as much. So now we have a directed graph. And again, our goal is going to be to find a set of bad edges such that if you remove the bad edges, now you have strongly connected components. And you want those strongly connected components to have small diameter. So basically, I want to find a set of bad edges such that if I remove them, all of the strongly connected components in the graph have small diameter. And I'm only going to guarantee small weak diameter, meaning that if I have a component for any two edges in the component, there exists a path between them of weight at most d. But that path might go outside the component. That won't end up mattering. So for intuition, you can even think of it as strong diameter. This won't really make a difference. Okay, and note that this is weighted diameter. So what this means, when I say it has weak diameter d, it means for any 2 points in the component, the distance between them, the weighted distance between them is at most d. Okay, and then what does this look like? This now looks a little different because I said we remove these bad edges, and now we have a bunch of strongly connected components of small diameter. But there's a third set of edges because in a directed graph, if you have strongly connected components, you can still have edges between them. Like in an undirected graph, if you have a bunch of disparate components, they by definition have no edges between them. But here, even after you remove the red edges and you have these low diameter strongly connected components, there's still edges between them that kind of form a dag. So basically you have, once you remove the red edges, you have strongly connected components, and then you have edges moving in one direction. You can't have edges moving in both directions because then you get a larger component. So essentially, there are three kinds of edges. There's your strongly connected components that have small diameter. There's these black dag edges moving forward, and you can have many of them. And then there's a small number of these bad edges which move backwards in the topological order. That's what you end up with. And again, the bad edges, we show up, I'll upper bound the probability that a particular edge is bad. Okay, so let me know if there are questions about what's going on in this decomposition, because we're going to be using this a bunch. Yeah. Yes, no, the distance is this distance is in just the original graph. Yeah, so basically for any 2 points like these two, the distance in the original graph is at most d. Yeah.
Are there few components?
No, the only thing we care about is that there are few red edges. And then yeah. You can have many components with a very long path. Yeah, that won't end up mattering. Yeah. Okay, so the history in the directed case, it's this is technically new to our paper, but in some sense, it's not conceptually, it's not surprising. Like once you have the undirected thing, it's not surprising that you can do this for directed graphs. It's a relatively easy extension of this older paper for undirected graphs. So really our main innovation is not that this decomposition exists, it's how to use it. And in particular, note that this decomposition only works for non-negative weights. So it's a bit surprising that this will apply to our problem at all, because the hard part of our problem is the negative weights. We're going to see in a second why this decomposition ends up being useful. Okay. So let me just give a few easy examples just to give you a little bit of flavor of the decomposition. So if G is an undirected path, then what you do is you just pick a random number between 1 and d, and then you cut every d edges after that. So you cut at I, you cut at I plus d, you cut at I plus 2d, you cut at I plus 3d, and so on. And so clearly your components of size d, and also clearly every edge has a 1 over d probability of being cut, because it's just like it's only cut if you pick that I to perfectly align with the edge. Note that there's correlation. Right? If I cut at I 100% cut at I plus d and I plus 2d and I plus 3d. So these edges are not independent, but we don't need independence. We just need that if you pick one particular edge, the probability is at most 1 over d. Okay, the second example is if you have a cycle and you cut, then all you do is you just pick a random edge and you cut that. And then basically once you cut that edge, your cycle just becomes a bunch of singleton strongly connected components with a bunch of edges between them, but that's like a dag path. So that's why I'm saying it's okay to have a lot of edges as long as they only move in one direction. But then you only have one edge moving in the backwards direction, which is the edge you cut from the cycle. And again, that edge is unlikely. Any particular edge is unlikely to be that edge. Okay. So how are we going to use low diameter decomposition? So again, we cannot run it on the original graph because the original graph has negative edge weights. So we're going to have this graph where we basically round up all the edge weights to 0. We're going to run it on that graph. So after we run low diameter decomposition on this graph, as I said, there are now 3 kinds of edges: the edges inside the component, the dag edges, and the backwards edges. So now what we're going to do is we're basically going to just fix those one by one. So first, we're going to find a price function such that all of the edges inside the components have non-negative weight. Once we found that price function, then we're going to take the new graph where everything in here is non-negative, but you have negative weights on the black and red edges, and we're going to feed that to phase 2. And phase 2 is going to find another price function, which will maintain all of these being non-negative, but will also make sure that the black edges become non-negative. And then in phase 3, we're going to find another price function, which makes the red edges non-negative. So we're basically going to deal with these 3 classes of edges separately. Yeah.
But we should understand the black and red edges to include the negative edge weight.
Yes, yeah, absolutely, yeah. Right. So this is somehow when I say make them non-negative, I mean in the original graph. This graph is only used to originally run the low diameter decomposition. Okay, let me give an intuition for why these 3 phases, why this might be helpful. So, as I said, we have these 3 phases which fix these 3 classes of edges. So phase 2 is going to be by far the easiest, just because here you're just dealing with dag edges, and dags are really easy to deal with, as we'll see. This is like essentially trivial. Phase 3, the intuition is that we said that any particular edge is unlikely to be in Esep. And so what we're going to be able to show is that if you look at any path, it's going to have, in expectation, few edges from Esep, just because every edge has a low probability of being in Esep. The point is that once you get to phase 3, you've already fixed all these edges, and you've already fixed all these edges. So the only edges in your graph that are still negative are these edges, because you fixed all the others. So basically, if you can show that every path has a small intersection with Esep in expectation, that means that every path is going to have few negative edges, because the only negative edges are the ones in Esep. And if you have few negative edges, then you could use this trick that I said, that it's easy to handle paths that have few negative edges. So that's intuition for why phase 2 and phase 3 are easy. And phase 1, at this stage, it's very unclear why phase 1 would be easy, because phase 1 is saying, in phase 1, you want to fix the edges inside a component. But remember, these components are defined in terms of this positive graph and in terms of like positive diameter. But once you look at the actual graph, the component can have a bunch of negative edges. So it's sort of unclear why a component having small positive diameter would help at all. And that's going to be the thing that we have to talk about, like why it's easier to deal with a component that has small positive diameter. Okay. So before I sort of move on to the algorithm, I need one more kind of basic preliminary, which is essentially all of these algorithms are at some level using weight scaling. So basically, what we're going to do is, I said before that we want to find a good price function. That's not exactly what we're going to do. The basic subroutine we want is to take a graph where the edges are negative and make them less negative. So take a graph where all the edges are like bigger than negative 2b and find a price function where they become at most negative b. And the point is, if you can solve this green box, you're done. Like all you need to do is solve this green box, because if you can solve this green box, what you do is you just start with your original graph and you keep calling the green box over and over again. So your edges become less and less and less and less negative until they're like some tiny negative number. And then you can basically show that if they're a tiny negative number, they are not impacting your shortest distances. Because remember, this is not changing your shortest paths at all, because you're just applying price functions. And the original graph weights are integral. So you have some graph with basically integral distances. And now you've applied this price function. So if you have a tiny negative number and your original distances are integral, then the tiny negative number just will not, they can't add up to 1. So they basically can't affect your shortest distances. So the idea is, if you can do this green thing, you just keep scaling down weights until they're tiny, and then you can round them up to 0, and now you have no negative weights. That's the basic idea. Yes, our probabilities were weight. Yes, yeah. So I mean, I'm gonna brush that aside a little bit in this talk, but D can actually be pretty big. D can like depend on, in the full version, D can depend on like the biggest edge weight. So D can still be pretty big. But Yeah, but this will allow us to focus on a single weight scale. So yeah, we just have to solve the green part basically for the rest of this talk. And in fact, to make things simpler, and this will keep D small just because I want to focus on the simple case, I'm going to focus on a particular weight scale, which is if your weights are at most in your original graph, the weights are at most 2, and you want to find a price function such that they become at most 1. That's the goal. Actually, all the weight scales are the same. Like the algorithm really, this is not easier somehow. It really looks exactly the same. It's just easier to think about because you have specific numbers. So yeah, from now on, for the rest of the talk, you have a graph where the weights are most 2. You want a graph where the weights are most 1 by finding a price function. So here's going to be our general plan. Okay, so we're going to have this graph G plus 0, which is just the original graph plus a dummy source. And then we're going to define a new graph, G plus 1, which is going to be the original graph, but we're going to add 1 to all the edge weights. And then also add a dummy source again with the 0 edge weights to everything. So G plus 1, basically just the original graph, and you add 1 to all the edge weights. And so our goal is going to be that we're going to find a perfect price function for G plus 1. By perfect, I mean it's actually going to have non-negative edge weights everywhere. The clicker gets flickering in and out. Yeah. So we want to find a price function on G plus 1 that actually has non-negative weights everywhere. So it's like the perfect price function. And the point is that then if you apply that same price function to G, then you'll have what you wanted where all your weights are bigger than -1. Just because G and G plus 1, just all the edge weights differ by 1. So if they're all non-negative in G plus 1, then they're all bigger than -1 in G. So the point is that we've kind of reduced our goal to finding our overall goal is the scaling, but we've reduced that to finding a perfect price function in this G plus 1. And you might ask, why is G plus 1 easier to work with? Like why I'm saying, okay, instead of finding a price function in G, we're going to find one in G plus 1. And it might be totally unintuitive why G plus 1 would be an easier graph to work with than G. All you did is you added +1 to all the edge weights. And this is sort of where the kind of key intuition comes in, which is, okay, so again, this is just repeating what we have, or our goal is to find this perfect price function for G plus 1. So here's the intuition, which is that we're going to compute our price function by computing shortest distances. As I said before, if you can compute shortest distances, you can compute a price function. And we said before that it's easier to compute shortest paths if the paths have few edges. And if you think about what G plus 1 is doing, at a very high level, it's penalizing long paths. It's penalizing paths with many edges because you're adding this additive error on every edge. So in G plus 1, you're sort of encouraging your paths to have fewer edges. And those paths are going to be easier to find. That's a very informal statement. Here's a formal statement that I'm going to prove later in the talk, but I want to state it now, which is basically, let's say I have a graph and the diameter, meaning the weighted diameter of that graph, is at most D, meaning just the distance between any two vertices is at most D. Then I claim that if I take a dummy source, so S prime here is a dummy source, then I claim that in G plus 1, so in G, your only guarantee is that between any two points, you have a path of distance at most D. But then if you look at G plus 1 turns out to have this very nice property that every path actually has at most D edges. And so this is why low diameter decomposition is going to be useful, because basically this we're going to guarantee by low diameter decomposition. We're going to sort of decompose our graph into these connected components of small diameter and then work inside each component. And the point is, inside each of these components, if we then turn to G plus 1, our paths are actually going to have few edges. And then we're going to be able to use Bellman for it. So again, I'll come back to this later, but this is just to give a preview of why G plus 1 is going to have nicer properties than G. Okay, so I'm just going to say the 3 graphs we're going to use, and then I'm going to actually go and talk about our algorithm. So again, we have this graph G plus 0, which is just the original graph, and we're going to use that only for analysis. Then we have this graph G plus 1, which is the main graph we're going to be working with, and we want to find a perfect price function for G plus 1, and that's going to give us what we want. Finally, we're going to have a graph G plus 2, which is just add 2 to all the edge weights. And the reason we need this is just because G plus 2 has non-negative edge weights, right? Because we're assuming this top level weight scale where we start with a graph where everything is -2. And so now if you add +2 to everything, everything is non-negative, and so you can use your low diameter decomposition. So that's the only reason we G +2, so that we can run this low diameter decomposition. This is our graph of non-negative weights. Okay, so and again, the key goal is to find this perfect price function for G +1. So let's see how that's going to work. So as a warm-up, I'm going to give an algorithm that's slow. It's like m root m. So this was known before. But this contains like 95% of our ideas. So once you see this, it's quite easy to get to the next step of improving it to near linear. And it's just going to be easier to think about. Okay, so to repeat, again, this is our goal. We're trying to find a perfect price function for G +1. And the first thing we're going to do is we're going to run low diameter decomposition on this graph G +2. Again, the only reason we want G +2 is because all the edges are non-negative. We're going to run it with D equals root n. So we have a bunch of components of diameter root n, and all the bad edges are bad with probability, like their weight over root n. Okay, so now I said we're going to have 3 phases. In the first phase, we're going to find a price function such that all the edges inside the components become non-negative. In the second phase, we're going to find a price function such that all the black edges, the DAG edges, become non-negative. And in the third phase, we're going to find a price function that makes all the edges non-negative. So basically, we're going to fix the red edges, and the green and black edges will remain fixed. So now everything will be fixed. Okay, so as I said before, I think phase 1 is the your weights. So right. So we are making the assumption that the negative weights are not, because we're just scaling down the negative weights. The positive weights can be enormous. Yes. So those big edges will just be cut automatically. But an intuition to think about is that, let's say I have a edge of weight n squared. That edge can basically never be part of a shortest path that has like, we only care about shortest paths if total weight is negative, because essentially we're trying to compute distances from a dummy source. So if all the weights in the graph were positive, then from the dummy source, the shortest path would just be 0 everywhere. So if the graph has, like, if you have an edge with enormous edge weight, it just won't really figure in any shortest paths. That's the intuition. Yeah, so you really end up not caring. But yes, if it has weight root n, it'll just definitely be cut 100% of the time. It'll always be a red edge. Yeah. Okay. So as I said before, I think phase 1 is by far the least intuitive, and fortunately, it's also the first, so we can do it right away. Okay, so where are we? So we ran this low diameter decomposition, and now we're focusing on some strongly connected component in this graph. It's in G minus Esep. I mean, the strongly connected components are the same. The graphs just differ by weight. So I really should have said G here, because the edge sets themselves are the same. So strongly connected component, strongly connected in all of the parts. Okay, so we're focusing on some particular strongly connected component, and our goal is to end up with positive weights inside that particular component. So here is a weak claim, which is that we know that our component has weak diameter less than or equal to D, or square root n, just by definition of the low diameter decomposition. So here's a really easy claim, which is that because the component has a weak diameter less than D, for any 2 vertices inside the component, we know that the shortest path between them in the original graph with original weights can't be too negative. It can't be greater than negative G. So it can be negative, but not too negative. And the reason is just, otherwise you would have a negative cycle. And we said there's no negative cycle in our original graph. That's it. So no, you only need a weak diameter. It doesn't matter if the path from Y to X goes through other parts. The point is, in the original graph G, the definition of this component is that there exists some path from Y to X in the original graph of length at most D. So there can't be any path that's more negative than negative D, because otherwise you would have a negative cycle. Okay, this on its own is not that useful, because again, we said that what's easy for us to compute using Bellman-Ford-Dijkstra is paths with few negative edges. But this does not at all guarantee that the path has few negative edges, because the path could be like 1, -1, 1, -1, 1, -1, 1, -1. So it could still have a bunch of negative edges. But as I promised in G +1, you're actually going to have few negative edges. So here's the strong claim. So again, we're starting with this component that has weak diameter less than d. We're picking a dummy source, and I'm claiming that every path has at most, every shortest path has at most root n edges. Every shortest path from the dummy source. And here's the proof. So I have my dummy source f, and there's some path from s to y. It starts by going to some x, and then it goes to y. Okay, and note that again, by the setup, we know there's a path from y to x in the original graph of length at most d. Okay, so the first thing I want to say is that the weight of this path in G+1 is at most 0, because we're picking the shortest path from a dummy source. And if the weight of that path is bigger than 0, then the shortest path from the dummy source would just be to go directly from the dummy source to y. So this is basically the reason we want to work with the dummy source, because we only want to care about negative paths. So, okay, we know that that path has to have negative weight. But that's in G+1. This is the shortest path in G+1. That's what we're looking at. So if it's negative, if it's negative in G+1, then it's even more negative in G, because in G you have -1 on all the weights between G and G+1. So basically in G, that path has to be like more negative than the number of edges on P, because you do -1 for every edge. So this is what I was saying. Basically, the longer the path is, the more negative it will be in the original graph. Okay. On the other hand, we have that between y and x, there's this path at length at most d, and that was actually in G+2, because we did low diameter decomposition in G+2. So if in G+2 the weight is at most d, then in G this orange path is definitely at most d, because in G weights are only shorter. And now we're basically done, because again, we can't have a negative weight cycle. And so we know that in the original graph, the distance from x to y has to be more than negative d, otherwise we'd have a negative cycle. But we also know that this distance is more negative the more edges you have on this path P. And so you know that the weight of that path in the original graph is bigger than negative d. And so the number of edges on that path has to be less than d, because otherwise by step 2, if you have more than d edges, it would be too negative. So it's just kind of like a, basic argument. Okay, so we can see in G+1, all our paths are short. They contain few edges. And this is exactly what we wanted. So basically now, once we have this claim, we can just compute all the distances from the dummy source by running Bellman Ford for d iterations. So we can compute it quickly because you only have d paths. And as before, once you can compute distances, you can automatically compute a price function by just setting it to be that distance. And so now you're going to have 0 edge weights everywhere inside the component, or non-negative edge weights, sorry. And the total running time is just like, for all the components, is like MD, because you're running Bellman Ford for d iterations on a bunch of disjoint components. Okay, so that is phase 1. You do this LDD, and then for every dummy source, for every component, you just pick a dummy source and you just run Bellman Ford for root n iterations. That's the whole algorithm. The point is that Bellman Ford within root n iterations will actually find all the shortest distances, because you know that all the shortest paths have at most root n edges. Okay, great. So that was the hardest phase. That was actually, the other two are more intuitive. So in phase 2 now, we want to, so all the edges inside here are non-negative. Now we want all the black edges to become non-negative. So how do we do that? We're just going to call this function fixed dag edges, which basically, if it takes a graph where if all the edges inside the components are non-negative, then it creates a new price function such that the dag edges between them are also non-negative. And it's really, this is essentially trivial, where, so this is the graph you start with, right? Everything inside the SCCs is non-negative, but the step between them can be negative, the dag edges. So you put the SCCs in topological order, because again, all these dag edges are moving in one direction, so you can find the topological order. And now basically you pick some enormous number L. Think of L as like bigger than the absolute value of every edge in your graph. And you just set your first component is nothing, and then the next component, set all the prices of all the vertices inside this component to be negative L. The next one is negative 2L. So your components get more and more negative as you go. And now the point is that if you look at any edge between two different SCCs, the later endpoint is going to have like a much lower price. And so when you look at the reduced price function, right, the reduced price is like the original edge weight plus the starting potential minus the ending potential. And this is going to be more negative. So you're basically adding at least L. You could be adding more than L, because like if you go from here to here, you'll be adding L. But basically, you're just pushing all your edge weights on this DAG part by L. So you can make them positive by just setting L to be enormous. And then the edges inside the components don't change, because both points have the same price. Okay, so as I said, DAGs are easy. This is how you do DAGs. Finally, I want to go to phase 3. So where are we when we reach phase 3? All the edges inside here are non-negative. All the black edges are non-negative. Only the red edges are negative. And now we want to somehow find a price function that makes the red edges non-negative. So yes, yeah, your red edges are now in, like, you now have 0 structure on the red edges, basically. All the other edges are fixed. They can be super negative, yeah. Yeah, they can be very big negative numbers at this point.
They get hit a lot.
Exactly, they get hit, yeah, exactly. So like whatever weights you started with, now the red edges are extremely negative, but that ends up not mattering. Because this algorithm Bellman-Ford plus Dijkstra that works well if there are a few negative edges on the path, that doesn't care about weights at all. So we're gonna basically find exact distances in this graph in G+1. And so all the prices, yeah, so it doesn't matter. The weights no longer matter, basically. Yeah, okay, so you have these red edges, they can be super negative, but all the other edges are good. And so now, so as I said, by the time we enter phase 3, only these edges in Esep can have negative weight. And remember that every edge is in Esep with a low probability. It's like the weight divided by root n. So, and recall that we have this algorithm that works well as long as the number of negative edges on a path is small. So the point is we can argue now that the number of negative edges on a path is any particular path is going to have a small intersection with the red edges, just because the red edges are red with small probability in expectation. And since only the red edges can be negative, that means that every path in expectation has few negative edges, and so we can compute it efficiently. So that's going to be, so in particular, what we're going to show is that for any vertex, if you look at the shortest path in G+1 from the dummy source to that vertex, that shortest path has a small intersection with Esep. And then we're done, because that means that since Esep are the only negative edges, you have a small, like, that now means that every path has at most root n negative edges in G+1. So now if you just run Bellman-Ford plus Dijkstra on this graph, you can find all your exact shortest paths from the dummy source. And by setting those prices, you get non-negative weights in G+1. Okay, so this is the key claim we need to prove. And I feel like I don't have that much time, so I'll kind of, basically the intuition is extremely easy, which is just that, so the intersection with Esep of your path, right, is just basically the weight of that path divided by root n. That's just this probability. So all you want to do is you basically want to upper bound the weight of the path. But this is easy because basically we know that in G+1, the weights, like the path is by definition less than 0. Like if you have negative weight, like in G+1 has negative weights, but the overall path is less than 0 because it's the dummy source. So in G+2, it can be higher, right? We kind of looked at this graph with only positive weights, and so your probability of cutting edges is higher, but it's still at most like n. Because you're just increasing all the edge weights by 1. So basically the weight of this path is at most n. Each edge is cut with probability weight over root n. So you're basically cutting root n edges on the path. That's the proof. Okay, so that essentially completes. So this is so basically in phase 3, you just pick a dummy source for the whole graph, and now you just run this Bellman-Ford plus Dijkstra, and the and you're only going to have n over d negative edges on the path. It's like the weight is at most n, and you're cutting everything with probability 1 over d. So overall, it'll take n with n.
Didn't you say in the beginning that the thing with d and the h number of negative edges was constant degree graph?
Yeah, constant degree graph, but you can, it's really without loss of generality, you can add a bunch of dummy vertices and dummy edges. You can.
You told them for the diameter,
You don't need that, but if you wanted to, you could turn it into a dummy tree. Yeah. But yes, it ends up working out. Yeah, without any trouble. And you don't even really need the constant degree thing. That's just for simplicity. It's somehow, if it doesn't have constant degree, you have to define it a little more carefully. But it's more a hack than like a deep thing that you need. Okay, so this was M root M. And I want to very quickly talk about how do we improve this to actual nonlinear. So this was our algorithm, right? You do load decomposition up to some D. Then you have phase one, where in phase one, all of your SCCs have diameter at most D. And we said that means that in G+1, all the shortest paths are going to contain at most D edges. And so your runtime is MD. And in particular, basically, the bigger D, the worse the runtime, which makes sense. I mean, if your component is enormous, then it's not really easier than working with the original graph. Whereas if your components are small, then your shortest paths are going to be small. So basically, the bigger D is, the harder phase one is. Phase two is going to be easy no matter what. And phase three is the opposite, right? The bigger D is, the easier phase three is, because big D means that every edge is cut with probability 1/D. And so you're cutting fewer edges and you have these fewer red edges to deal with. So there's a trade-off between phase one and phase three. So that's why we set D to be like root N in the easy version. So here's what we're going to do instead. We're going to set D to be really high. So now phase three is going to be super fast. Every edge is cut with like this extremely high probability, extremely low probability. There are basically going to be no red edges. But now in phase one, all you can say is that the shortest path has at most N/2 edges. So running Bellman-Ford is not going to work well. But from a different perspective, we started with a graph where every shortest path has at most N edges. And now we ran low diameter decomposition. We're focusing on a single component. And now that component, every shortest path has at most N/2 edges. So we've halved the number of edges. And so you can actually just apply this recursively, log n times, and it keeps halving the number of edges. And then in the end, phase one, you're going to have components with very few edges, and those are easy to solve. So let me give kind of the pseudocode. So we're going to define a new parameter in our recursion. So we want to solve this scale down, which goes from -2 to -1. But now within, so basically there's this outer layer where we're scaling down the weights, but now I'm focusing on a particular scale where we're going from -2 to -1. And here again, we're going to have log n iterations where we're going to be bringing down this parameter delta, where delta represents the number of edges on the shortest path in G+1 from the dummy source. So delta is like the number of edges on a path. So originally delta is n, and we're going to define this general function such that it takes this graph with this parameter delta where all shortest paths have at most delta edges, and it's going to reduce the edge width. And so basically the idea is that our initial call, we're just going to call it delta equals n, because clearly every path contains almost n edges. So this is always a valid call. And then this is going to recursively call itself with smaller and smaller parameter delta. Okay, and the base case is easy because when delta equals 1, your shortest paths have at most one edge, or even if delta is a constant, your shortest paths have most a constant number of edges. You can run Bellman-Ford, it's easy. Okay, so basically in phase one, we know that, so now when we do low diameter decomposition, it's actually going to depend on delta. So basically we're going to set our diameter to be like delta over 2. So delta is the number of edges on every shortest path, and we're going to set our diameter to be delta over 2. And what that's going to guarantee in phase one is that every component in G+1 we said has at most D edges. So now it has at most delta over 2 edges. So we started with a graph where every shortest path has most delta edges. Now we have a graph where every shortest path has most delta over 2 edges. How do you solve it for delta over 2? Well, you just call it again with the smaller delta parameter. So this just ends up calling itself log n times. There's nothing really hidden here. This is like really what the pseudocode looks like in the paper as well. You just by definition call the same function with smaller delta and it'll solve your problem. And then you have a base case where like when delta is constant, you just run Bellman-Ford. Okay, in phase 3, basically what we can show is that every shortest path contains something like delta over D edges. And delta over D ends up being constant. delta over d of these bad edges from ESEP. And the reason is that we're dividing by d because every edge in ESEP is cut with probability 1 over d. So where's the delta coming from? Well, if you remember, I said before that basically we care about the weight of the path. And we said in G plus 1, the path is non-negative, just because you're working from a dummy source. And so in G plus 2, the weight of the path is basically going to depend on the number of edges on the path. So if the path has few edges, the weight of the path will be smaller. And so that's why there's this dependency on delta. Okay. This is the algorithm. This is basically the end of the technical part of the talk, and I'll just go through like a minute or two of like open problem steps. Okay. Yeah, so just to repeat in phase 3, because we know every shortest path contains few edges from ESEP, only the edges in ESEP are negative at this point. So that means every shortest path has few negative edges and expectations, so we can run this combination of Bellman-Ford and Dijkstra, and we can find the shortest. Okay, so to recall, this was our main subroutine, and we sort of then, like at the higher level, we have this outer scaling subroutine, and then inside each scale, we scale down delta. And if you can solve this green thing, you can solve the whole thing by just scaling down weights over and over and over again until they're tiny. Okay, so let's talk about just summary and open problems. So this is our result. And so basically, right, the history was there was this classic Bellman-Ford, and there were these combinatorial improvements, and then there was these sort of improvements using much heavier machinery, and we basically get a faster algorithm that also uses much more basic tools. So in terms of open problems, there are kind of two categories of open problems. There's open problems about specifically shortest paths. So one really big open problem is that if you have arbitrary edge weights, Dijkstra's is really quick, but we actually don't know how to solve it if you have negative weights. Like Bellman-Ford is still the best if you have like real valued edge weights. Like they're not integers, they're not polynomial. We don't know how to solve this.
This step log b is something that...
Yeah, that's not known either. Yeah, definitely. If you could get like log of the highest weight, that would be also very new. Like every algorithm for this problem, including like the min cost flow, they're all just using a basic scaling at the highest level. So nothing, no technique is known beyond that.
But it's pretty easier to do to get m log b than to get a sort of log where you straight through the box.
Yes, I agree. It is strictly easier. But so even like getting like m n to the 2/3 log b, I think would be very new. Like no one has any idea how to do that. Like, yeah. So the second is, I kind of said before, one of the reasons to have kind of simple combinatorial algorithms is they're more likely to extend to like parallel setting, distributed setting. And so we haven't actually done that. That was just an abstract claim. I think our algorithm will extend. If you kind of look at all the steps, they seem like the kind of things that can be parallelized. In particular, the low diameter decomposition for undirected graphs is already known how to make it distributed. For directed, not yet, but we think we can do something here. But there's still work to be done. And finally, you know, it's at this point, like in some sense, we've matched Dijkstra's. We have near linear, but we have like 8 logs. You can try to reduce the logs. I know some other people have already told us that they've gotten rid of a few of them. So yeah, those are the kind of 3 main things that remain. But I also want to talk about a general open problem, which is, as I said, kind of like there are these really fundamental graph problems that are really simple to define, and yet currently we have this fast solution using min cost flow, but it's like a very involved solution to solve what are some of the problems are really simple problems. And also like to solve like something like bipartite matching, currently we're using an algorithm for min cost flow, which is like a much harder problem. And so the question is basically, for some of these problems, if you could come up with simpler algorithms. And for me, at least, the really big question is unweighted bipartite matching, because it's such a simple problem to define. It feels like it shouldn't be that hard, but somehow, in terms of like, like simple combinatorial algorithms, the best is still like M-Root-N from a long time ago. And so there's a question of, is there a way to solve this problem? Or do we really need, maybe we really need this heavy machinery? It's unclear. So that to me is an open problem. Yeah, that's it. Thank you, everyone. Yeah. Oh, right. So what, I don't remember the exact formula. Yeah, I've seen some of these, but yeah, yeah.